In this lesson, we are going to look at a probability model known as the geometric model. There are three main things that have to be present in order for you to use a geometric model. Okay? It has to be an example of a Bernoulli trial, meaning your situation has to fit the following three conditions. It has to be binary, where you have a probability of a success and a failure. So flipping a coin is a Bernoulli trial. Rolling a die can be considered Bernoulli. You could say, what's the probability of getting a 5 or 6? Well, that would be 2 out of 6 would be a success, and then a failure would be 4 out of 6. The next is I for independent trials. This means that the first trial cannot affect the outcome of your second trial. Now, we are going to see some scenarios where this gets violated. For instance, whenever you're sampling without replacement, technically you're taking something out. You are changing the sample space, so you are altering the probabilities. So if that occurs, if you're dealing with a small enough sample, you can still proceed. This is known as the 10% condition. Okay to sample less than 10% of the population. You'll also see this written as little n is less than 1/10 of capital N, meaning little n is your sample size, capital N is your population size. Finally, let's say that stands for same success, which is my way of saying the probability of a success has to be constant. So I use a little p to denote the probability. And then let's talk about when we use a geometric model. So we're using it whenever we are looking at how long it will take to achieve the first success in a series of Bernoulli trials. How long it will take to achieve the first success. So if it's how many times would you expect to have to roll a die until you get a 5? In the textbook, you read a scenario about Tiger Woods cereal boxes. How many times would you have to open a box of cereal before you expected to pull a Tiger Woods card from the box? Here are the different formulas that you are going to use when looking at geometric distributions. I encourage you to find them on your formula sheet. This formula, I will show you how to do it by hand and also on the calculator. Our expected value, again, is going to be mean, and our standard deviation is over here. They'll all make more sense in context. So let's start by looking at a scenario. The probability that a randomly selected person is left-handed is 13%. The first question is what is the probability that the first left-handed person is the 5th person we meet? So it's kind of standing out to me that this is possibly geometric because we're saying the first left-handed person, so the first time it occurs, is the 5th person we meet. So let's make sure that this is a Bernoulli trial. So is it binary? Do we have two outcomes? So you're either left-handed or not. Would it be independent? Yeah, the probability that your first person is left-handed won't affect probability of the second person. 1 minus p, so a failure would be 0.87 because 1 minus 0.13 is 0.87. You'll notice that your textbook uses a Q rather than 1 minus P. The AP formula sheet now uses 1 minus P, so I'm going to try to switch and always just say failure is 1 minus P. The complement, in other words. And I should probably define what my random variable is. Remember, it's got to be a number, so it's the number of people selected. It's the number of people selected until I select a left-handed person. So the first question here, using proper notation, what is the probability that the first left-handed person is the 5th person we meet? So I'm saying that capital X is equal to 5. So I'm defining my lowercase x, one of my possible random outcomes, as 5. Now, by hand, we could figure out this probability. We've done problems like this before. So this would be like the first person is not, would be 0.87. The second person, not left-handed. Third person, not left-handed. And fourth person, not left-handed. And fifth person is the first one is 0.13. Toss that in the calculator and I get 0.0745. But because I have now identified that this is geometric, I can actually do this on my graphing calculator. So I'll show you the series of buttons to hit. Geometric probability on a calculator, you hit second vars, it's hidden in distribution. And if you scroll down, or actually it's easier to go up, there's two options, geometric PDF and geometric CDF. PDF stands for probability density function, and it's when you're trying to find the probability for one specific value. Finding the probability that the first left-handed person is the fifth, so x equals 5, you're going to use geometric PDF. You would use CDF if the question were at or below 5, standing for cumulative cumulative density function, excuse me. So this option would be used for the probability that the first left-handed person is the first, second, third, fourth, or fifth. So it sums all the values at and below 5. Okay, but so we're going to use option E. When you do that, it's going to ask for your p-value, which is the probability of a success, which we know is 0.13. And then our x value is our random variable equal to x. And then just select paste, and it calculates that probability. So if you were showing your notation of how you did that on the graphing calculator, you can just write what you see on your screen, where you're doing geometric PDF, and then in parentheses, you can see over here on the calculator, it kind of shows you what you need, the 0.13, but you got to mention what that is. That's P equals 0.13, and your X equaled 5. And that is approximately, again, 0.0745. Lastly, this may be overkill, but I want to show you, the formula works here as well. So I could have taken my formula and just kind of substituted probability, capital X is equal to 5 is equal to 1 minus P is 0.87 to the X minus 1, well, to the fourth power, times P is 0.13, and that's exactly what we just logically reasoned through. So sometimes you'll even find that teachers don't even really teach this geometric model because it can be done by logical reasoning. Part B says, what's the probability that the first left-handed person we meet is after the fourth person? So this is saying, what's the probability that our random variable is greater than 4? Now here's the issue with that. We have like an indefinite amount of people. You're going to go up to 2 million. You're not going to be able to do that. So this is where you're definitely going to need to use your complement. So this would be equal to 1 minus the probability that X is equal to, well, that it happens on the first person or the second person, third person, or the fourth person. So by hand, you could calculate each of these ones separately. So I'm going to help you reason it through, and then we'll look at what are some shortcuts. So it'd be 1 minus, now I'm going to just put this in brackets here. So if it happens on the first, it's 0.13 chance, plus not on the first would be 0.87, but on the second. And then plus not on the first, not on the second, but on the third. So I did 0.87 squared. You have a success on the third, okay? And then on the fourth, you have your success. So that means doesn't happen on the first, doesn't happen on the second, doesn't happen on the third, would be to the third power times 0.13. So you can, let me just close my brackets there. 1 minus that, throw that in my calculator. That's going to be 1 minus 0.4271 approximately, which is approximately 0.5729. How could you do that in the calculator? Well, this could be 1 minus geometric CDF, okay? Because CDF is going to let's do 0.13 would be P, and x would be 4. Okay, because what would cumulative density function do? That's going to sum your probability for 4 and below. So you're doing 1, 2, 3, and 4. So take a second and put that in your calculator and you will see that you get 0.5729 as well. And there's yet a third way that I can think through this problem. So for some of you, this might be painful getting multiple ways, but you're going to latch onto whatever logic works best for you. So what's the probability that the first left-handed person we meet is after the fourth person? So another way of me saying this would be the same as me saying what's the probability that all 4 are not left. So the first is not, and the second is not, third is not, and fourth is not would be 0.87 to the fourth power, and toss that in your calculator, and that's 0.5729. So honestly, in my brain, this logic here is easiest. Probably the calculator is second place, and then what I wrote in red is probably the most complicated, but might be easiest to follow. And we're asked, how many people do we expect to see before we get our first left-handed person? So when I see this expect to see, that's telling me I'm looking for an expected value, and an expected value is the mean. So I'm going to use my formula. Mu of x is equal to 1 divided by p, and that's pretty simple math. I just plug in 0.13, and in my calculator I get approximately 7.69 people. So I would expect 7.69 people before I find one left-handed, recognizing that this is, of course, an average, which is why I'm getting a decimal. Okay, let's go through a more complex example where we address our conditions, we use our formula, and practice good notation in context. So it says, Postini is a global company specializing in communication security. The company monitors over 1 billion internet messages per day and recently reported that 91% of emails are spam. I believe it. Let's assume that your email is typical, meaning 91% spam. We'll also assume that you aren't using a spam filter, so every message gets dumped in your inbox. And since spam comes from many different sources, we'll consider your messages to be independent. All right, so here's our questions. Overnight, your inbox collects email. When you check your email in the morning, about how many spam emails should you expect to wade through and discard before you find a real message? So geometric model should jump out at you because it's how many before the first one you find, or until you find your first real message. And then what's the probability that the fourth message in your inbox is the first one that isn't spam? So there are some conditions we need to check. So first of all, B, is it binary? There are two outcomes, a real message, I'm going to say P is equal to 0.09, and 1 minus P would be 0.91. Next, I, independence. Well, we're told that the messages arrive independently. And third, S, we need the same success. So the probability P equals 0.09 is the same or is constant. Would be another way of saying that, is constant. Therefore, I can use a geometric model. Now, whenever I state that, I should always list my parameters. We want to get in the habit of doing this. And I just want to show you a little trick. If you ever get confused about what parameters do I need to use, look at your AP formula sheet. I just showed you a clip right here. It tells you a geometric model has a parameter P, so that it has 1. What is P? You're always going to want to name that. So therefore, I can use a geometric model with P equals 0.09, or just write P equals 0.09 right after it. All right, let me just move this. All righty. So let's define our random variable. Let's say let capital X equal, now it's always a number, so it's the number of, what are we doing? We're checking emails. Number of emails checked until I find a real message. We are asked how many emails should you expect to wade through and discard before you find a real message. So whenever we're finding expected value of X, that's our mean. So I grab that formula from my formula sheet. It's 1 over P, or 1 divided by 0.09. That is 11.1. And when I report the mean, I'm going to, it doesn't ask me about standard deviation, so I'm going to bypass that right now. The second thing it asks me is, what's the probability that the fourth message in your inbox is the first one that isn't spam? So what's the probability that capital X is equal to 4? Well, you can look at your formula sheet or logically think it through. So that means the first 3 are not, would be 0.91 to the third times the probability that the fourth one is, it's 0.0678. So let's put this in context. On average, I expect to check just over 11 emails before I find a real message. There's a 6.78% chance that my first real email will be the fourth I check. Our third example and final one in this video is people with O-negative blood are called universal donors because O-negative blood can be given to anyone else regardless of the recipient's blood type. Only about 6% of people have O-negative blood. Part A, if donors line up at random for a blood drive, how many do you expect? That's going to be your mean to examine before you find someone who has O-negative blood. What's the probability that the first O-negative donor is one of the first 4 people in line? So first we check B, is it binary? And I see that there are 2 outcomes. At first people are like, wait, but there's more than 2 blood types. But if we just say a success would be a person who is O negative, and that's going to be P is equal to 0.06, and a failure would be all other blood types. So that's going to be 0.94. I check for independence. And I would say that if you are taking somebody out to sample their blood, you're not going to put them back in. So this is not like sampling with replacement. So we need to address our 10% condition. However, as long as your donors are fewer than 10% of all other donors, it's safe to proceed. So we're going to assume that. And then we're looking same success. In other words, is our probability constant. Say that the probability of each donor being O negative is P equals 0.06 because the donors lined up randomly. So you're not worrying about families standing together where genetics takes changes your probability, would be another way of saying that. Okay, so let's say that I can model it with a geometric model because these conditions have been met. So I can model capital X with a geometric model, P equals 0.06. So I really need to say what capital X is. So I'm going to say let X be, it has to be a number, so the number of donors until I get somebody who is O positive. Scratch that, I mean O negative. Okay, so we're asked how many do we expect to examine before we find someone who is O negative. So expect, I'm just going to shrink this to give me more space to write. My expected value of X is equal to the mean of X, which is 1 divided by P, which is approximately 16.7 people. That's part A. Now, what's the probability that the first O-negative donor found is one of the first 4 people in line? So capital X is the number of donors until you find someone. So X has to be less than or equal to 4. which is meaning that the probability could occur where x is equal to 1 or 2 or 3 or 4. So if you're calculating this through by hand, chance it happens on the first try is 0.06. Plus, what about if it happens on the second? Well, that means it didn't happen on the first, but it did happen on the second. Plus, what if it happens on the third? Would be not on the first two, so 0.94 squared, but is a success on the third, plus on the fourth, 0.94 to the third times 0.06. Throw that in your calculator, or probably even faster than that would be to use geometric CDF, cumulative, where p is equal to 0.06 and x is equal to 4. So for CDF, it's going to calculate at and below 4. So it's automatically going to sum 1, 2, 3, and 4. Both of these will give you 0.2193. So whichever you like better. So my conclusion is blood drives like this can expect to examine an average of 16.7 people to find a universal donor. About 22% of the time there will be one in the first 4 people in line.